Anybody else has the proposal to read the subject? Now is the time. Somebody can coordinate for it. Now is the time. Online copy is fine, but if there's somebody who hasn't submitted, like take everybody up to it. Good. Are there any questions, anything we need to address? Anybody, any questions? It was the best class. No questions. Everything was done right. Excellent. So I think I stopped somewhere around here last week, and somebody can confirm the problem this slide. Yes, no, maybe. You stopped just the program. Yeah, I stopped. I think I stopped somewhere. At 24. 24. Well, that's true. So just recapping, we have the first midterm in 2 weeks, right? So I'll finish whatever I finished today, and probably there's a little bit left for next week, and that's the first midterm's material. And then anything after that, after the first midterm, goes to the second. Okay, so I guess now it's time for you guys to start studying if you haven't started yet. The format of the midterm is basically similar format to the quiz. There are questions, and I expect short answers to the point. You know, do not waste the whatever graphite in your or lead in your pencils or the ink in your other writing implement. If I ask the question, you answer the question. Usually the space that's there, it commensurates with how much I want as far as answer with a normal handwriting. As I see, some of you have a tendency to write a lot. That takes you a lot of time and doesn't score you too much. If it's right, if it's right. If it's not right, it could be 2 pages, it's still not right. Okay. No questions, nothing, so I'll continue with grounding. So it begs the question that, or the statement rather, that you might as well close the door. So it really begs the question that, you know, you're building an embankment above the foundation level, and you are building some kind of a dam, if you will, below the foundation level, of about the equal depth, right? Now, why would you want to do that in the first place? Why is the dam? Yeah.
To prevent water from flowing to the other side.
To prevent water from circumventing your dam and flowing under, right? So you come up with this grouting program that whatever you're building it on, you have to go at least that deep below ground, and it's easily achieved by grouting. What is grout? And this course is not about concrete materials, so general understanding of what grout is will be sufficient. So what is grout?
It's like adhesive to fill the gaps.
Yeah, but grout on its own, what is grout? Not its purpose, but what it's made out of. Sand, water, sand, water, cement, some kind of a cementitious material. Nothing more. So it's something that's readily flows, can be readily pumped. So our idea is that we have this cementitious material that once it hardens, it becomes more or less impervious. Now, the problem we're facing with is that we have some kind of a bedrock, fractured bedrock at depth. We generally have no idea where the fractures are, how many, what their orientation. We drill a few boreholes, we look at the core samples, and that's pretty much it. So the rest is guesswork. So as I've shown it, and let me just go to that set of images from magazines. I've been showing this over and over. This one. So we know that this is where the actual core of the dam is going to be. So you see these red marks here, there's one there, up there, one here, probably one there, and so forth. This is where they drill down, and they're injecting grout in one hole, and they're pumping it, and they're pumping it, and they're pumping it, in the hope that it will come out at the other holes. I mentioned this earlier, of course, so just, trying to read that. So it is all in a belief that once you have a grout going on one hole and coming out of another hole, you grout everything in between. Now, oftentimes there is no grout coming out. And we talked about it the other day. What could be the reason? Voids in the rock. The joints go the other direction, you see like turn around, there's like a grout fountain down the slope, stuff like that. So there could be many reasons, it's simply because you just don't know which direction it's going. But what you're trying to achieve, that under the core, under the impermeable core, you want to have something like a curtain of impermeable material, and it is achieved by grouting all the joints, discontinuities in the rock. That's at least the general idea of what they're trying to do.
See this paper? Just demolish the rock.
So if you have a 100-meter tall dam, you would need to excavate into rock 100 meters down. What do you think of the cost of that? How much? They would probably outright abandon the whole thing. So this vertical curtain, sometimes a single staggered layer, as I was kind of showing it the other day. If I have the proposed, and this is a plan view, this is the proposed core, so they drill down in a staggered fashion, pump through this one, and they're monitoring these two. If nothing happens, or for added security, they might end up with another row of holes drilled and another row of holes for monitoring. So they pump and they make a double, even sometimes a triple curtain at depth, just to make sure that hopefully all the discontinuities are filled. So that's the vertical curve. Underneath the core itself, air transitions, that's filter zones. They seal the fractures with fissures up to about 3 meters of depth. So that would be what you see on this photo. That now they have this, basically they pour a concrete cap, and if you see there's even rebar, just to control any loose rock or anything. So there is no chance of any of the rock wedges or blocks dislodging, that could potentially lead to differential settlement and all sorts of troubles. So again, like I said, in essence, they are pouring a concrete kind of cap over the terrain, and this is pretty much washed down up to maybe about there. You see some loose rock on either side, so this will probably eventually get cleaned off. But if you look at the general area, the topsoil is being removed all the way. So if I look at the whole dam site from the top, and they're constructing the dam, so the bottom of it is there, and right now the top is there. You see that the rock being cleaned out on either side. Pretty much the whole footprint of where the dam is going to be. So remove any chance of loose material, anything that can slide, consolidate, or whatever. Okay. Now, in addition to that, prior to placing the core, they fill all the fissures, fill all the cracks with something called dental concrete. It's fairly fine, cementitious material that really gets a kind of level surface for the dam to be filled. Now, the very important thing is that the first lift of the core has to be placed and compacted with hand. Why would that be the case? You know, I think I drew something like this last time, that maybe this is the profile of the ground. Why would you need to hand compact it?
To make a roller, to make sure that it really goes into the irregularities.
I mentioned. But if you were to just place the material on and you have this roller running back and forth, this will get compacted much more than that will get compacted. So you want a good compaction, because if you end up with a pocket of relatively uncompacted material that can settle downwards also, it can create a more permeable pocket that runs along the length of the dam or across the dam, whatever, that defeats the purpose of having the dam in the first place. And also, if you have the hand compaction with handle cappers, then you can really get into those small areas, fill them up, make a uniform level, and from then onwards start compacting. Core thicker to overcome any inconsistencies in placement. So if you over-design it, it has a greater capacity to retard flow of water. So, make sure that it's done right. Plastic cores are better than brittle cores. Now, I don't mean plastic as in, this kind of plastic, right? What kind of a plastic do I mean? Yeah, plastic material that actually deforms, yields, as opposed to anything that would be brittle, because if it breaks, it leaves cracks, it leaves joints in there that are pathways to water. So you want the material that it deforms. Generally, everybody knows what OMC, optimum moisture content, is, right? Maximum dry density and optimum moisture content. Everybody knows it? No. So, for general granular material, you have moisture content versus density. Depending on moisture content, there is a point that gives the highest density for a material. It's from basic soil mechanics. So you would want to go from 1 or 2% within of the optimum moisture content. So when you place the material, it is at its densest. Because if it's not at its densest point, then if you place more material on top of it, it will densify, meaning it will settle. And you have not designed for this settlement. So it's key that you want to place it as dense as possible. More plastic material across, or rather adjacent to your abutments. Why would I want to do that? Yeah, I mean, think of it as abutments, like a sloping material. So if this would be again brittle material, as it settles down, it will end up with cracks in it and pathways for water. If it's plastic, it will deform and kind of take the shape of the actual abutment. And slope the sides of the core to reduce arcing. We talked about this, right? What's like the shell is holding down the sides of the core. Not providing correct? Filter transition zone, clean homogeneous sand. Remember, this is the grain size that goes between the clay size particles of the core and the much larger particle sizes of the shell. So it serves as a filter, right? It does not allow the migration of the clay size particles into the voids of the rock. Crack stopping, crack filling, we talked about this. So, not much new there. Narrow graded multiple zone filters, particularly against rock fill. It's all dysfunctionally graded material as the flow of water across the dam. You don't want the smaller particles to get embedded in the voids of the larger particles. Now, this is for the downstream phase. Why would you have similar gradation on the upstream phase? They give the large particles, intermediate particles, and small particles. Why would you have that? So again, just to recap the idea here. So you have the core, you have the transition, and you have the, I guess, the rock shell. So from here onwards, and this is downstream. Here onward, it makes sense. Smallest particle size, intermediate, largest particle size, right? So the small cannot migrate into the voids of the big one because of the transition sizes in between. But why would be the case the other way around? The large rock particles would not migrate into the voids of the clay. So, anybody?
By the migration of the small particles in the core, it will be
Exactly. Right? That's why it has to be non-cohesive and lightly compacted. If there are any cracks developed in the core, the material, the water is flowing this way, the material here would wash into the crack and basically support the weight of everything above it and stop the propagation of the crack. Vertical drains, crack stopper in a homogeneous dam. Remember, a homogeneous dam is the inside-out dam. That the more permeable material is in the center, and a shell is made out of all more permeable. Now, the construction, even though it would be okay to have something that's say 1 meter wide for the transition zone, generally it's 2 to 3 meters wide. Why is the 2 to 3 meters a magic number? Think of it, let me just go to the other figure here. Why would the 2 or 3 meter wide is the minimal width of any of these zones? Yeah, that's sort of typical width of the equipment, right? These are placed and then compacted inside, or on site rather. So that would be the minimum. If this made like 1 meter wide, then it would be really difficult to find an equipment that can sort of compact it in such a narrow width. So the minimum would be the minimum width of the equipment that's available to do it. So size-wise, the reason for sand is concrete, or sorry, the concrete sand, due to its microstructure, it will be able to catch most clay-sized particles. that can't really wash through. Remember, this concrete sand would be similar to the roller compacted concrete, but instead of aggregate, you're using sand. So it's a mixture of cement, sand, and some water. And in addition, bituminous paving sand, which would be paving sand with instead of concrete or instead of cement, they add some bitumen. Something that's fairly impermeable. Couple of specification values for the filters, or basic soil mechanics, coefficient of uniformity, is sort of the width of the narrowness of the grain size distribution curve, and permeability should be so many, at least so many centimeters per second. So 10 to the minus 2 centimeters per second. So it's a decent permeability. Seepage control, one thing to remember, it's easier to control than to prevent. We do not have the ability or the amount of money to build something that's completely impervious. And it's not the case. As long as we control the flow of seepage or flow of water through the dam, we're okay. We design it for so many cubic meters per day per meter of the dam, and if we treat that water and discharge it or collect it, pump it back, whatever, we're okay. However, if we have unexpected seepage, we have these extra measures added as vertical drains on the under the downstream core, blanket or finger drains as we showed in, I guess, the first lecture. And finally, once you have all these drains emerging, let me just go back and show it to review. We have these blanket drains and filter drains. And at the very end, when these emerge, this bottom layer emerges at the downstream toe of the dam, and there should be some kind of a highly permeable material running across that takes it away from the dam, from the foundation, and goes to the treatment facility. Erosion control, we talked about it, I believe. Just you see a lot of things throughout the course, and they're done that way, that there is a good amount of repetition. Various facts pop their heads up at various places. And there's a good reason to that, because quite a few of the features built into an embankment dam, they serve multiple purposes. And they come into play when it comes to, for example, riprap or erosion protection. You have to sort of devise some kind of a measure to protect the downstream slope, and also it has to provide some means of, if you have the rainwater falling down on it and running off of it, by providing some kind of a filter underneath it, you're not washing out the fine grain material if there is any under the erosion. So it's part of a one large system, and again, if I go back and sorry for flipping back and forth, but I sort of imagine that getting close to the midterm, it's a good time to review concepts. So when we go to one of these embankment dams, that multiple parts play together, and each and every has its own place. So for the downstream erosion protection, it is protecting the material that's comprising the downstream shell. Now we talked about it, that it would be possible to place an upstream some kind of erosion protection, and why would we need that upstream erosion protection? After, well, something that occurs in conjunction with an earthquake. Yeah, waves, right? Wave action. Be that from wind, be that from earthquake, be that from whatever. So we can now install this erosion protection, similar one, the ones on the downstream or the upstream slope. Most of it is submerged, but it serves a purpose.
Excuse me.
Yep.
Could you repeat what the reason we put on the upstream side?
Erosion protection. From
Okay.
wave action due to earthquakes or wind or whatever that whips up waves. Because waves come and they wash the material off. leakage around pipes mentioned earlier. Do not put pipes either intentionally that serve a purpose or basically pipes like this of uncompacted material. So if you have any spillway or if you have any drainage gallery or whatever to the dam, put it somewhere to the side. So if there are any issues, you can control it as opposed to putting it through the dam, where it will cause problems. Now, it's a good job for junior engineers. These pipes are half a meter thick or a meter thick, and they have to be inspected. So that's where they send the junior engineers down with some kind of a lamp, let them crawl through, and if they don't come out, then they just hire another one. So, but joking aside, they're designed such that it would be possible to inspect it visually, either by somebody going through or sending some kind of a robot or something like that to allow inspection. Collars at entry and exit points, simply because if I have some kind of I'm going to sort of draw it from a side, so if this is the pipe that kind of goes through the dam, I'm providing this collar on a surface that's kind of grouted around, so it doesn't let water to flow beside or under or over the pipe. It's kind of like a collar, very similar to what you see on, say, roof chimneys or something like that. These boots to prevent water from getting in and through around these various pipes. Seismic consideration. We do have to appreciate that earthquakes happen. Quite often these dams are built in earthquake zones, and if they're shaken, they will get damaged. That's nearly impossible to build a structure that will not get damaged. Now, the funny thing is, and I'll ask you why, among the dams, embankment, earthen embankment dams, quite a few of them, or most of them, actually survive an earthquake that, say, another arch dam or gravity dam would break or fail. Why do you think there is a reason?
They are able to move with the waves.
Okay, so think of it that way. The earthen dam is made out of, well, earth, right? It's deformable. So when it's shaken, it deforms as the waves go through it. Its stiffness is much less than a solid large block of concrete, which is, stiffer. If you start shaking it, stresses develop. It cannot deform readily, so the only thing it can do is crack. So the same idea, a couple of examples, that they haven't really deformed that much to break or collapse unless the waves, again going back to the wave action, the waves caused by the earthquake were so great that they overtopped the dam, so water started to flow on top of the dam, ran down the downstream face and eroded the slope, made it steeper, and that led to the collapse of the dam. And a couple of examples. So these are not the direct result of an earthquake, but the earthquake whipped up the water in a reservoir, and the water started flowing on top of the dam and down the downstream slope. Had they built the dam higher or had the water level lower, the dam should have been fine. Hydraulic sand-filled dams are susceptible to damage. What would be the problem with sand that's saturated in a case of an earthquake? Yeah. Those are the most or the highest potential for liquefaction. Why would that be the case?
The water pressure increases, and that makes the sand to be able to.
Yeah, basically, if you have these sand grains touching each other, the soil skeleton, right, it is carrying the weight by effective stress to the contact. Now, when you add water to it and the water pressure increases because it can't flow out, then it pushes the particles apart, the particles are not in contact anymore, therefore the material behaves as a fluid as opposed to a solid, and loses all of its strength. So sands are the most liquefaction prone materials. So in one way they're good, they provide a lot of sort of permeability and strength, but once they're shaken and they're filled with water, they're really problematic. So generally it's been found that if you have a well-built dam, it can take up to 20% of the acceleration due to gravity. It will withstand it. That corresponds to about a magnitude 7 earthquake. So it can take a substantial amount of earthquake and it will survive. Of course, same idea goes here. Sands or silky material that's saturated and it's not compacted. So you would have the dam itself that's okay, but the foundation would liquefy underneath it. And at the end, it's the same result, right? But different causes of failure. So what we can do, the obvious one, well, don't build a dam where there are earthquakes. Now, oftentimes that's not the solution. Avoid soil susceptible to liquefaction. That's potentially okay, but it could be costly if you need to excavate a lot of materials. Over-designing, mentioned earlier, had those dams been higher or the water level been lower, there would be no overtopping. So if you build them higher, you provide higher or more freeboard, it would be okay. Internal drainage, so the problem with liquefaction is the water pressure, core water pressure. If the water can drain when it's subject to these earthquake winds, then the water pressure will not build up, it will not push the particles apart, and it will not liquefy. So if there is enough drainage inside the dam, it should be not a problem. And thick transition zones, if I have high water pressure gradient, it will build up and cause liquefaction, similar to the point before. If I have more drainage pads, that would relieve the core water pressure. Thick plastic, non-brittle, erosion-resistant core for multiple reasons. So the same idea of having a plastic core now comes back for multiple reasons. So can anybody list at least 2 of them? Why would we use a plastic or non-brittle core?
It deforms as opposed to crack.
Yes, it deforms as opposed to crack. Number 2 is fairly low permeability. Number 3 is relatively easy to place.
Settlement differential settlement control.
So there are many reasons for this. Why then the core and the abutment? To improve foundation contact. So if you look at these abutments, you make them wider here in that direction, so there's more support as it's settling. The area of contact in and out of the flow cord is larger. Slope stability, and here the funny thing is that I'll show a slide from another course. I'll tell you the story. So the stability of the slopes when you're designing an embankment, then automatically you think both the downstream and the upstream slope that you have to design is such that it's stable, right? That's the logical. However, you would have to investigate the slopes in a reservoir too. So this particular dam, well, it's not really a dam failure, it's a reservoir failure. It occurred in the late 60s in northern Italy that they had this arch dam, right? You can see the nice arch concrete dam and a reservoir behind it. Now, what would these white areas be, particularly this one? What's the indication Why are they white or light colored?
It's new.
New, what do you mean new?
Like it has some suffering erosion, and it's not
Erosion
old,
or
it has
what
some-
else?
There was a previous sliding.
Yeah, it isn't evidence the scarring is evidence it's either erosion or there was a previous slope failure, slide. Now, at the time when they constructed this dam, they did a wonderful job of the dam, but they didn't do such a good job of assessing the geology of the reservoir itself. So the situation, particularly note this mountain, and now you can see the before and the after picture of what happened, but you know, the situation was as follows. So you have the mountainside, and somewhere at depth there was a relatively deep sea. So you have good competent rock on either side, and this might have been a clay-filled gouge or something like that. It could be like this thick. So you have a kilometer of mountain on top and this thick clay. So the problem was that before constructing this embankment, or this dam rather, the mountain was stable. Once they started filling up the reservoir, what happened? Yeah. The toe got inundated, water was able to migrate up, and everybody knows from this equation what's the effect of water pressure increasing that we see.
Increase the shear stress.
What did it do?
It decreases the effective stress and decreases the shear stress.
It increased the pore water pressure, that in turn decreased the shear strength. So what happened is that this mountainside basically slid down into the reservoir. So you have this kilometer tall mountain sliding down, and this is the end result. So where the reservoir was, it got filled up with rock. And we're talking about millions of cubic meters of rock. Now, what's the funny thing if you look at the before and after picture?
There's a dam before the dam.
True, but you said it, but it's the first part.
did not survive.
Yeah, the dam is still there. It didn't crack, it didn't fail, it didn't do anything. So basically, you think of it just like when you're jumping into the bathtub and there's too much water in there. What happens to the water? It comes out. So same thing here. Instead of you, it was a mountain that went into the bathtub. Okay, so the moral of the story is it's not only the dam and its slopes if it's an embankment dam, but rather the slopes in a reservoir. I mean, this could be like tens or hundreds of square kilometers, depending on the size of this reservoir. So it could be a huge job to map out, identify any of the potential slides. And then the other interesting thing was that if this weak seam ever daylighted on the top or the crest of the slope, it would have not been visible because of the vegetation. So if people didn't know or didn't look at the geology of the site, they wouldn't know that there might be a deep material thousands or hundreds of meters below the surface. But like some of you identified, these white scars are potential earlier slides. So if there was a slide earlier, there might be a slide later, depending on the condition. And just for the sake of completeness, the dam was somewhere up here in a valley, a little picturesque Italian town before, no town afterwards. So if you see some buildings up back in the distance in the hills survive, and also on the other side of this little stream coming down, but the rest of it was completely wiped out by this flowing water mixed with boulders and soil and trees and cottages and whatever it was able to scour and pick up. But still, if you look at it from the geotechnics, the dam itself performed marvelously. It was never designed to withstand the shock wave of water slamming into it and jumping over it and running down. Where the slope behind it is a completely different story. So going back to our first slides. Any fractured or loose rock abutments has to be either grouted if possible or removed. So that was another little picture from the set of slides that wrong course. Some of you interested in rock climbing, I might have mentioned, we might find a job like this. Again, rock climbing is the paid job. Anybody into rock climbing? Maybe you get like. So anyways, what do you think that these two guys are doing there other than enjoying the nice scenery? Huh?
Ceiling fractures.
Either ceiling fractures or maybe they have some kind of steel bars and they're prying open and down any loose rock. It's better to come down in a controlled fashion than come down later in an uncontrolled fashion. So they scale this, and this would be the proposed abutment. So maybe they're hanging somewhere here on the side or up there, or maybe even there, or perhaps there, and systematically going from left to right, top to bottom, and picking off anything that's loose. And that's for the purpose of being able to either grout or remove any of the loose material that may, under an earthquake, fall into the reservoir or damage the dam, get displaced, move within the embankment dam, and so forth. Of course, the ultimate solution would be build another dam downstream. If the first one fails, well, hopefully the second one will come. That would be the ultimate seismic prevention. Okay, but obvious reasons it's seldom done. So that would be this set of slides. Any questions about this set of slides? So now I'm going to cover the last major topic before the midterm, and that is going to be monitoring dams and slopes. So it seems like I'm a little bit ahead this year, maybe because you guys are not asking any questions. But still, by looking at it, there are 12 slides, so whatever I finish today, then that would be the end of the material for the midterm, and what I start covering, then I guess either starting today or starting next week is going to be the material for the second. Okay? Like anything else, just like kids, dams should not be operated unwatched. It's not enough to build a dam and fill the reservoir. It has to be monitored at all times. It's almost like a living thing. There's the water level inside. There might be various instruments on the dam or on the abutments or the slopes. Things like inclinometers, which is basically a rod that's installed into the dam, and it's tipped and sticking out is survey, right? So there is a survey station somewhere sitting up at a fixed location, not on a dam, And every day or every week, they survey the tips of these inclinometers. Why would they do that, and what do they get out of it? So let me just sketch it. If this is a mountain, or this is maybe the dam, let's make this a dam. So if this is the dam's cross section, they have maybe one here installed, maybe there is one there installed, and maybe one there installed. So somewhere where they can know a fixed location, there's the total station, and they measure the location of this point and the other 3 points. Why would they do that, and what do they get out of it?
They monitor the secret. If they have a abnormal change in the fluid levels, they know that the core is maybe about to crack.
Well, they're monitoring any deformation due to whatever reason, right? Due to settlement, due to excessive water flow, whatever. So if they measure the exact location of those points on a regular basis, they would know what the dam is doing. But there's something called a borehole inclinometer that think of it this way. I'm just exaggerating. You drill a hole, you case it with a plastic material, you put a cap on it, and every week you come down and you put a long straight rod down. And you pull it out, and you come back the next week, you take this long rod, you shove it down, you pull it out, and you keep doing it. What do you get out of that?
Exactly, which is where
The height of the water level inside
You could if it's instrumented such that it detects the water level. No, this is a straight piece of metal, no instrumentation on it. They shove it down the hole to the bottom. If it's good, they come out and come the next week.
If it's the core is fluid. People that have
Yeah.
a break.
So, if some deformation, I'm going to draw another one, there is a deformation in a dam, and it looks now something like this. The dam is kind of, the top part is moving. How would they detect it? Yeah, the rod couldn't go any deeper. The rod has, length. They shove it down, they measure 2 meters sticking out of a 10-meter rod, so the problem is 8 meters below the surface. I'm just telling you, showing you a very simple example, but it can get really sophisticated. But idea is that any inclination, any change, any movement would be detected within the dam. Yes?
that might be like really close for fighting, right? Since it's like goes to
Yeah, but this is vertical and the hole itself is about this. And it goes borehole inclination. There are all sorts of things. There's some electronic ones that are left in there. I'm just trying to give you the idea. So I guess he's looking it up on the internet.
No, just take them out.
Okay, let's look it up on the internet. If we have it, might as well. First. So devices like that, so you get a good idea. There's one that slides down, and it has an accelerometer in there, so it measures direction too. So this one can go all the way down. I just showed you the simplest one, the $5 one. So this one slides down, and it detects, you see the angle from the vertical. If this was the original one, it actually now maps out how it's deformed. There are all sorts of sophisticated ways. There would be a similar one that measures the inclination. Fine. If it's straight in the other direction, if it has some kind of a sliding on it, it would be now bent, and it's detected right away. So if there are a couple of these in the dam itself, another idea is that they're measuring it, and these are the figures that they're getting. So if there's any downhill movement, it will be readily detectable. Another graph, various displacements. If you do this on a regular basis, you have a time history of what the dam is doing. It's displacing, what way, in conjunction with measuring points. And of course, there's nothing to stop you that some of these might be monitoring wells in which, for example, this has a couple of locations, I believe, that they can monitor any slope movement. And like I said, in conjunction with that, you can have wells, like somebody said, that you can measure the water level. So you know exactly where the phreatic surface is at any point where there is an observation. So monitoring, going back to the course's theme, monitoring is a fairly important part. Of course, it has to be like as simple as this rod, no high-tech stuff. You have a hole, you put the rod down, and it gets stuck there, something happens at that level. This time and age, oftentimes remote logging, i.e. no person has to walk the dam, but everything is connected wirelessly to a central location close to the dam, to your office if you're the site engineer, and you have pretty much real-time data of all the monitoring systems. And of course, once in a while, junior engineers have to be sent out. So the things that can be monitored summarize: seepage, as it was mentioned, deformation, both for settlement and also for slope stability, groundwater pressure, temperature is important, right? If it's in a permafrost area of northern Canada, seismic events, and so forth. So putting all this together into one table, the various methods on the sort of the vertical axis, and the horizontal axis would be the various phases in a life of a dam. So from the site investigation, design, to construction, operation, and perhaps long-term performance that goes beyond the life of a dam. So groundwater level at the site prior to construction, the easiest one would be to have a bunch of piezometer holes or locations, holes, and measure. Permafrost temperature, any thermistor or any device that can measure temperature and it could be embedded at any point, pretty much throughout the whole time or whole lifespan of the dam. Frost depth, stage construction of dam cores. Remember, you have to protect the core from frost damage because any water within the fine-grained core, it could expand when these ice lenses are formed. Then when it thaws, the ice lenses result in voids and frost problems. Yeah.
But what can you do if you realize that it's the core is freezing? Like, you see the temperature of your thermistor, and then you see it's about to get frozen. But what's the solution?
If it is in a working, operating dam, right, then you probably find the engineer who put their stamp on it and sue them. I mean, think of it that way, that at that point you realize it was not done properly. It shouldn't. But in that case, you would need to excavate this damaged core, replace the material, recompact it, and rebuild everything that was on top of it. But while it's being constructed, remember that these things are built in layers, if you will, in these lift stages. So wherever above the core it's left exposed and the temperature is such it can freeze, you need to protect arching blocks of styrofoam or anything that's sort of insulating materials. And how do you indicate this? Some kind of a chemical, metal in blue, no clue. I think it turns color when it's exposed to a certain temperature. That's what it's used. Seepage, internal erosion, piping. You don't have it at the site investigation stage or the construction stage, but when it's operation, piezometers, visual inspection, water level, wear monitoring, and so on. Settlement, piezometers, surveying, which is using a total station to survey a bunch of points, extensometers. What would extensometers be? It's in their name.
Is it like in drilling, when you're just like measuring how much there was before?
Yeah. So if I have a fixed location somewhere here, whatever, this is a fixed location, and I run a cable to that location, and if this moves in that direction, then this will extend the cable, right? So I can measure the movement relative. Now the problem is that if they're getting closer, then the extensometer doesn't really work that well. So under certain circumstances, it is good, but generally, if you can measure it with a total station, then it doesn't really matter if it's moving away or coming close. Stability, pore water pressure via piezometers, any slope downhill movement would be via surveying, inclinometers, crack gauges. What are crack gauges? That's exactly what it says. Crack gauge. Yeah. There are these little device, you can think of it like little sheets or little finger-like pieces of metal of known thicknesses, so you open them up and you shove it in a crack, and whatever the right width is, that's the width of the crack. So if you have one of these cracks on a crest of a dam or an abutment or something like that, and you come every month and you measure the width of the crack, you would know where the crack is opening up, closing up, whatever. And visual inspection, basically walking the dam, is, as you see, it appears at many, many places. Condition of filters and drains, pore water pressure. You can't really measure them or look at them, assess them if they are buried, right? So if by measuring the water pressure in them, it gives an indication of how permeable they are and they're sort of fulfilling their function, or if you have any access to any of them, visual inspection is the best. Ideally, in this time and age, there is nothing preventing you from taking photos, videos, or something like that, and that will serve as a permanent record of what's the state of the dam is at any given day or any point in time. So photographs, and ideally it should be done by the same person. If I go there and look at it, and if you go there and look at it, you see different things than I see. Our perception of the state of the dam is different. If it's the same person does it every time, then they have this sort of incremental comparison. So, if you get one of these jobs, hopefully they don't fire you because they want you to do it over and over and over and over to be consistent. Right? So monitoring, visual inspection is very important. So what should be done in these visual inspections? Soft zones and sand boils along the toe. What is a sand boil? Yes. What's causing it?
High hydraulic gradients.
Yes, basically that's the downstream end of a pipe to the dam. Water is coming out under high pressure, you have sandy material, you have a little fountain that's kind of bubbling out, boiling basically. So generally it is known that when you have these sand boils appearing at the toe of a dam, that means that the factor of safety of the slope is really close to 1. Right? So that's when you see one, you start running. Okay, so that's a direct indication of piping, washout type, that there is material, not just the water actively washing through the dam or being washed through the dam through these pipes and conduits. Same with dirty, sediment-laden water seeping out. So what would be the indication of water that has a lot of fine grains in it coming through your dam? Yeah, so the core is being washed out, so the transition material is not working properly. That would be a direct indication of a serious problem. Increased seepage rates, all of a sudden the collected water at the toe drains is much more than what you saw last week or last day or year or something like that. So the dam is more leaky and probably there is not so good reason why that's the case. Longitudinal cracks along the crest, right? So if I look at the cross section of the dam, and there are cracks on it that go in this direction. So it's a direct indication that the slope itself is moving downwards, whereas this one is staying, so it's tearing away from it. Tension cracks. If there are transverse cracks across the crest that go this way, that means that the dam along its length is settling at a different rate and it's tearing it apart along the length. If there is general settlement, all of a sudden the water seems to be higher when you're walking on the top of the dam, and you know that the water level has not increased, which means that whatever you're standing on is lower now. And that could be due to settlement and so forth. Bulge in the lower part of the dam, then the area here now, as opposed to being like this, it moves something like that. So it means that the material is going downwards and outwards. It could be as simple as settlement that was designed for, or it could be an indication of slope instability or any other more serious issue. Okay. Continuing, condition of spillways or any structure that's there to deal with any excess water that's in the reservoir. If those are clogged, there are perhaps some kind of washout type of a failure that they get eroded underneath or besides them. All of those need to be assessed. Condition of the riprap, erosion protection. If it's not there, of course, that could lead to erosion, oversteepening of the slope, and potential failure. Find the bunnies and dead trees and count them and have rabbit stew or whatever for lunch. So, any animal life and rules we talked about it. And I hope that there is going to be a presentation about any of the projects. Anybody doing roots and animal holes? Oh no, we're not gonna have pictures of rabbits. Oh. Other ways of monitoring piezometers. So the simplest one would be a standpipe, which is basically a perforated hole that allows water in. You lower this little gizmo that starts beeping or showing a signal when it touches water. So it could be a standpipe or something more complicated for low permeability soils, some kind of an electronic device. Monitoring deformation, settlement could be from these tool stations and these sort of monuments that you can measure. There's some product called slope indicator, which is like a trade name for these rods that stick out that can be surveyed. Let's see, slope indicator. What does internet show us those? Probably it has to be more broad. That would be another sort of inclinometer one. Saw the photo. Runs down, measures the orientation. I'm looking for that with this. So they have these rods with little stations in them, and as they deform, they change their electrical resistance, and that sends the signal back. So what it does that between these joints, and there are like links that can deform at these joints. So any of these links changes its orientation, it sends the signal, and you can monitor it. Find another. Can even have satellite monitoring, but I don't see it. Oops. Temperature for frost susceptible materials, and finally what you should put in a report. So these are guidelines of at the end of the day when you look at the dam, you will need to record the reservoir level and also the water level and any of these kind of tail water level where it's flowing out, so you know how high the water was in the dam, weather conditions, any conditions of these drawdown facilities, that the drawdown facilities are there in conjunction with the spillways, relatively rapidly lower the water level in the reservoir. Cross section of the dam, so you can indicate whatever observation you noticed. Geology, faults, access, the general age, design parameters of the dam, any plans for abandoning it, and comparison of any of the previous investigations or inspections that you can note what the differences are. Hence, it's good for one person to do it. Right? So this would be generally what your report should include at any given time. Okay? So I guess it's the end of these 12 slides, so let's have a break. 15 minutes. I guess since you guys sat down, probably means I should start going. So you just to reiterate on it, that up until now, that is the material for the first video. Starting with this one, this goes to the second video. Okay? Avoid any further questions on top. Brief introduction of what is meant by the concept of safety. Because ultimately for these dams, which are comprised of two slopes, the upstream and the downstream, plus the slopes in a reservoir, ultimately what you have to design them for as far as stability is concerned is the stability of the slope. Right? And the stability of the slope, the stability itself is assessed by using something called a factor of safety. And its simplest form is nothing but a capacity of the system divided by whatever demand is placed on the system. Right? If I divide the capacity of something by the demand placed on it, you get the factor of safety. So if you think of it that way, that you have a 1 liter bottle filled with water, so its capacity is 1 liter. If you're thirsty, your demand is, let's say, 1.5 liters. So what's the factor of safety of that poor water in the bottle? I have a capacity of the water bottle 1 liter. I'm really thirsty. I want to drink 1.5 liters of water. That's my demand. So it's 1 divided by 1.5.
0.67.
So the factor of safety of the water is, I guess, 2/3, 0.667. So it's less than 1, which means that the demand cannot be met by the capacity of the water bottle. Okay? Now, on the other hand, if I'm not that thirsty and I go with 0.5 liter of a 1 liter water bottle, then what is the factor of safety of the water? Yeah, it's basically 1 divided by 0.5, which is 2. Okay? Everybody clear by what I mean capacity and demand? Now, when it comes to slopes and everything, we can formulate the capacity and we can formulate the demand multiple ways. It could be the capacity as far as the force that you put on top of the slope. It can be basically withstand, that's the capacity, and the actual volume of the force placed on it is the demand, if it's treated as a weight vessel. Or if it is more like a real material, then the shear strength of the material comprising the slope divided by the shear stress that due to its weight, due to any other external forces applied or whatever. Okay? Or it could be the sum of the forces trying to overturn it and fail it, by the sum of the forces trying to hold it up, divided by the sum of the forces that's trying to, fail it. Or moments for overturning it and so forth. But still, the ultimate measure is it is the capacity divided by the demand. Is everybody clear on it? And all these give rise to the factor of safety that is computed via a limit equilibrium method. So if I know how to illustrate a limit equilibrium method, would be something like this. If I have a block of 1 kilogram weight sitting here, what would I need to put there to maintain it being level? And let's say that the distance to the center of gravity is 1 unit. Yeah, I could put 1 kilogram, whatever, force. So it maintains equilibrium. Now, what happens if I put 1.1 kilogram? Well, it will tip this way, correct? If I put less than 1 kilogram, it will tip that way. Everybody okay with the simple exercise? Now, let me put a block underneath here. That when it's horizontal, it touches it. So, what happens now if I put 1.1 kilograms on it? Nothing. What happens if I put 2 kilograms? 10. 100. Okay. What if I put 0.9? 0.8. So it is basically a limiting equilibrium. Anything, any weight, let's call this F. Any weight that's greater than equal to 1 maintains the equilibrium, right? Any weight that's less than 1 it fails. So at 1 is the limiting equilibrium. Any force less than 1, the equilibrium is not maintained, and this thing flips down. Anything force greater than 1 is always in equilibrium. Everybody okay with this concept of limiting equilibrium in that simple example? So when I now go back to the slopes, so anytime that the demand is equal to capacity, it is at the limiting equilibrium. If my demand is less than the capacity, it is still in equilibrium. If my demand is greater than the capacity, it failed. So, the capacity and demand could be the ratio of forces, as I mentioned. It could be the ratio of moments, whatever, causing sliding, rotation. That's the driving or the demand. And the capacity is the shear strength or forces or whatever that are trying to resist failure. So going to the simplest slope stability problem would be something like this. So if you think of it that there is a slope and there is a block of, say, rock sitting on it, and the inclination of the slope is alpha, the weight of the block is W, and what else we need? That's pretty much it. So the big question is, what is the weight that I can place, or the weight of this block, so it does not cause failure? That's the question. She will tell us, what is the weight of the rock? Just kidding. So that's the question. So how would this block fail?
Weight exceed the friction resistance.
Okay, so we do have to appreciate that there would be frictional resistance developed along the base, right? Let's call it P. Okay, so when this frictional resistance is exceeded, the block starts to slide down. So in the simplest case, I would be able to take a component perpendicular, so that would be the normal component, and there would be a component of this force along that sort of that direction. Let's call that P. So I would have, if I just zoom into this bottom, I would have the normal component versus the normal component due to weight, and I would have the sort of the shear component P and the shear component T. So everybody agrees that from basic statics, the two normal components will be the same, right? Action equals the reaction. But in this case, my question to you is, formulate the factor of safety equation. What?
E over T.
What is the definition of factor of safety? Capacity divided by demand. Capacity is whatever shear resistance the surface can provide. P would be the whatever demand or the driving forces, or the forces that cause failure. Many, many names for the same quantity, but in most generic form, it would be the capacity divided by the net. Everybody okay with this simple example? That every time P is less than T, it's safe. It doesn't move. As soon as P is equal to T, it is at its limiting equilibrium. And as soon as P is greater than T, it fails. Okay, so the factor of safety from all this, I can express it that if I put the capacity is equal to the factor of safety times the demand. Right, so this number tells me how much over the demand is till it actually reaches the capacity. So if I say a slope has a factor of safety of 1.3, what does it mean? Yeah, that the capacity is 1.3 times bigger than the demand. Right? So the limiting condition comes from this little exercise of this seesaw. When it's 1, failure is imminent. If it's less than 1, it's fail. Now, one little mental exercise that you sort of have to believe me is that can we have a factor of safety for a real slope that's say 0.95?
Yeah.
Real slope. I'm standing at it, at the bottom of it, and I calculate that its factor of safety is 0.95.
That's fine.
I'm just standing at the bottom of it, so tell me if it's bad or not bad. It's bad. Okay? So, go along with this little mental exercise. You calculate that it's 0.95. Okay, so the slope is still standing, yet your analysis says its factor of safety is less than 1. It should have failed. If it's still there. Why is it still there? There is some reason.
What's your
So what you say?
A body will go more hard to move and a friction is have a peak before the peak.
Just theoretically, the slope is there. You calculated a factor of safety of 0.95. There could be many reasons. Just to give you.
Maybe the soil parameters are wrong.
Yeah, your estimate of the material properties are not accurate, and you made an error on the safe side. Right? Okay, what else?
Because of the slope angle.
So you didn't measure the slope angle right. That's what you're saying. Yeah. Your measurement of the geometry of the slope is not correct. What else? There are roots that are stabilizing the slope that you did not account for in your analysis.
moisture level is lower than expected?
Yeah.
So
We don't know where the phreatic surface is. You estimated it to be higher, and it's lower. Okay? Keep going.
the soil is not as homogeneous as you expected.
Overall, it's all the uncertainties that you have in your calculations that backfire.
Yeah, so all the uncertainties in estimating soil properties, water level, whatever, are actually not as critical as you thought it could be. What else? You're using the wrong equations. are some former undergraduates here. Maybe you remember I have this question on the final in soil mechanics where you have to analyze I believe it's an infinite slope. I know you're blocking that out there. So anyways, the thing is that I discovered it years later after I had it the first time, that I provide a formula sheet. So the actual solution involves, and this is what I tell the class, that I provide the formula sheet, you provide how to use it. Right? You have to know what formula is for what case. So it so happens for solving that problem, you have to pick the right formula and you have to rearrange it to work. Now, there is a formula with a similar value that you calculate, but it's for a completely different slope. So it so happens in the equation, like I said, I did not design the question intentionally that within the equations you have some kind of a trig function and the slope angle was equal to whatever the friction angle was. And here there's a factor that you subtract one from another. So it makes the bottom of the equation equals to 0. I think it's 0. Yeah, I think it's 0. So anyways, it leads to a division by 0. So the students who doesn't know what equation to pick, and they pick the easiest one because they don't have to rearrange it, they end up with a situation that they have no idea what to do with. Right? You know, like a division by 0 and that kind of stuff. So the moral of the story is now you remember it. I hope you didn't pick the wrong.
No, I got it right, but
I'm sure you have other students saying that it's impossible. Well, you picked the wrong equation. So going back to this, among many other things, not knowing the parameters and everything, you have to have the appropriate equations, appropriate slope stability method that represents the actual failure mechanism. Now, flipping the whole thing aside, can you have a slope in existence if everything was right? Right parameters, right equations, and you calculate it, you don't know what the slope is or anything. Can the slope exist if its factor of safety is 0.99999? No, right? It means that anything that's less than 1, even by the smallest amount, has to fail. And by failing, it means that the material runs down the slope, deforming, displacing it and everything, so it results in a slope failure. So that's another interpretation of this limiting equilibrium. From purely like theoretical consideration is that the slope exists up to and until its factor of safety is 1.000. And it's 0.999, it failed. So there should be no slope, given everything ideal, knowledge of properties and right equation and everything. It should not be in existence when it's less than 1. Yet there are slopes that are, calculated factor of safety for various reasons, less than 1, and they have to relate. It means that either you goofed up the equation or you basically don't know enough, you assume the worst condition, yet it's not that grave and stuff like that. But I want you to be clear on what I mean by a factor of safety, what is the limiting equilibrium with this little seesaw example, that, if you say it's a factor of safety of such and such, you have a good understanding of what is meant by that. Now, typically a slope is considered safe when its factor of safety is 1.5 or greater. Now, why would I say that? I just talked about it that it's fine when it's 1 or more. Yes. I mean, you don't design these slopes basically living on the edge. That it's like 1 and we're good. Right? You have to have it. If it's 1.5, then it means that it's 50% extra room for uncertainties. Not knowing the water distribution needs, the material properties. Perhaps later on you want to add something to it, build something on top, whatever, increase the load, whatever. So you have this wiggle room, and in this case it's it's a healthy one, 50%. Then that's what you consider safe. Now we will see in a moment in a set of tables of what would be an acceptable factor of safety depending on certain circumstances. Now, further expanding the vocabulary, some structures are more safe than others due to their nature, basically inherently safe. So if I have the same dam, let's say it's an embankment dam, same material, same everything, if I construct it on a rock foundation as opposed to soft clay, the rock foundation one would be inherently more safe because the foundation has much higher strength, it will not settle, it's perhaps much less permeable, and the list goes on. So same dam, two different foundation conditions, one is inherently more safe than the other. So going to this big table of things, there are a couple of pages, 2 pages worth of a lot of stuff. I use this in quite a few of my courses, but the moral of the story is, again, you can read it from the slides if you really want to when you're studying, but what I'm trying to show you is this last column, and can you guys read it in the back or no? You have it on your phone? Anybody else? You have it on a computer? Young lady back there, you have a computer? You can read it from there? Okay. Second row from the back, can you read it up here? I guess that everybody can read. Good. So, last column. We're talking about soil or heavily jointed rock slope, basically a slope failure, or a wedge type of a jointed rock slope, toppling failure, and if I go to the second set, zone or embankment dams, gravity dams, arch dams, these are the ones relevant to the course. So if we look at them, factor of safety should be greater than 1.3 for a temporary slope with a minimum risk of damage. So if I pile up soil for some reason, an access road somewhere, it should be there for 2 months. I'm likely using equipment, go back and forth. I'm okay with a factor of safety of 1.3. It's a temporary structure, light load on it. It's not a permanent. Right? So I'm okay with 1.3, I'm taking more risk, but probably to build it, reinforce it such so its factor of safety is 1.5, would cost a lot of money, but I'm going to demolish it in 3 months. So I'm okay with 1.3. Now for a permanent slope, 1.5. Right? I have something there that should be there for quite a few years, so I build it such that I 50% over design. And the same thing for those rock slopes, 1.3, 1.5. And if I go to the embankment dams, 1.5 for full reservoir or full pool with a steady state seepage. This is the operating condition. This is what I designed it for. So I'm 50% over design. Now, if I have 1.3 or greater at the end of construction, without any reservoir loading, without any seepage or anything like that, I'm okay with 30% over design, right? It's not what its final operating condition is. So 1.3 is good. If I have uncertain events that the water level in the reservoir is pretty much getting to the top of the dam, it's not a usual occurrence, right? An extreme situation. In that case, I'm with 1.2, okay. And if all sorts of bad things happen, there is flood or maximum reservoir, seepage, perhaps an earthquake hits at the same time, I'm very, very happy that the factor of safety is greater than 1, right? I mean, how often do you expect that there is a storm and an earthquake at the same time, and it's springtime and water is melting from the mountains and filling up the reservoir? Probably not that often. So in that case, you're really happy if the whole thing just survives. So these three values for the earthen embankment dams represent factors of safety and of the slopes for very different scenarios. So it's not only what the factor of safety is value-wise, but under the circumstances it should be maintained is important. Everybody okay? Same dam, different conditions, different factors of safety. Now, it is up to you as the designer to count all the possible loads that these embankment dams can experience. Earthquakes, seepage, foundation settlement. So you have to come up with these scenarios. There's no big book of dam design. You have to consider all the scenarios. It really depends on the site, on the project, on the type of a dam, and so forth. Right? But generally, guideline-wise, like this. And now if we now switch over to gravity dams, foundation failure, 1.5. When the reservoir is full or its operating condition, and so on. 1.3 at least mean for maximum flood, and greater than 1 for extreme loading, maximum earthquake, reservoir full, and so forth. Very similar for arch dams, 1.5 for foundation failure, 1.3 for maximum flood condition, and only other ones. Yet, if you look at these other scenarios that you can have, say rock fall, there is no factor of safety. Now, why is that? I know it's a little bit beyond the course, but think about it. It's basically boulder-sized rocks detaching from the rock slope, falling or sliding or tumbling down. Why there is no factor of safety for such?
Or accidental situation.
More specific. It's not safe, but it's not well defined. You can't really find each and every possible piece of rock that can fall off and then see its factor of safety, right? It could be from a grape size to an estimate size. So in that case, there's no unique, for example, for a case of a slope or even this block, you know the size of a block. Or if it's a slope, you know the size of a slope. So some mechanisms, there is no such thing as factor of safety. Or for example, toppling. It's really at the same slope, and I can draw a quick sketch of the same slope. Say you're designing a road, and it has to be put into some kind of a cut, and the rock itself has these joints, right? It's jointed rock. So I can have the cut to build a road, something like this. I'm going to make a cut here and put the roadway there and cars and whatever, or I have the alternative of making the cut on the other side. Two very different stability conditions. Can anybody comment on it?
Right side is safer. Because the condition.
Anybody else?
Are they on the same elevation?
Same elevation. It's like a mirror image. The only difference is that there are these joints in the rock going kind of upper right to lower left. Other than you, anybody else? Can you leave a comment?
Or you wanna have it on the right side, whether it was on the left side, they'll just slide on you.
Anybody else? Doesn't want to say anything? No. I guess she's just shy about it. That's okay. Anybody? Other thoughts?
I think that on the side case, the slope is more critical because the discontinuities are outcropping the face of the slope, but on the right is more safe or safer.
So generally we agree, at least those of you who said something. Yeah, you want to say something?
Yes, I want to say if the snow fails, it will fall into the left road, but if you build with the right one is
Okay, so those of you who said something, all of you realize that inherently this condition is less safe than that one. I mean, this can slide out, this whole thing can slide out, and so you know the stability. And if you look it up in the charts, perhaps it would be that one planar or wedge sliding of one of the structural features or joints, and you know you have a very good understanding of what the factor of safety would be. Just like this block deadlift here, this wedge has a weight, and there is going to be shear resistance developed in this joint. So if you find the balance and you find the factor of safety, right? It's relatively simple. Now, consider the other side. What if this crop or rock here cracks and it kind of falls out? What would these other ones want to do? That would fall into this real toppling, right? All these pieces now would want to bend down, right? Let me go to the extreme case and let's say that this rock is missing. So now you have these overhanging blocks that will perhaps want to bend down and crack from the top and fall down. There are toppling type of failures. One of my PhD students is working on such research. So there are toppling type of failures, but whereas on the left, you have a very good definition of what's failing and what's not, and how to calculate the factor of safety, even based on what we talked about for half an hour. One on the right, it's not that simple. There's perhaps bending of these various layers, cracking, there are no clear interfaces, what's going on, and so forth. So for this category, toppling type, no generally acceptable criteria for factor of safety and so forth. So very, very, very different. And the only thing I did, that I moved the road from the left to the right. That's the only thing I did. Very good? So you can read this table at your leisure. It has little tidbits that are relevant, particularly the analysis methods. This course I mainly spend about 70% of the time on limit equilibrium, slope stability analysis, and about 30% time using finite elements. The reason being is that limit equilibrium in this time and age is kind of antiquated. There's no clear definition of this limiting equilibrium condition. Because you have to appreciate that it's not made out of blocks, the surfaces are not smooth, particularly for soil slopes. You don't really know exactly where the failure surface would be and so forth. So in this time and age, the more sort of comprehensive way to look at it is do a continuum model using finite elements, say for soils. Or for rocks, use discrete elements. Whereas the limit equilibrium methods, the derivation, it is pretty much coming from soil mechanics. For the strength, more Coulomb to give the shear strength, and the rest is pretty much first year undergraduate statics, as you will see. So the limiting equilibriums, they're relatively easy to derive, which You may disagree in a couple of weeks, but they're relatively easy to derive. And still, most of the engineering offices, practicing engineering offices, rely on slope stability analysis using limit equilibrium methods for the simple reason being that most of the more senior people, they understand that because that's what they learn. If you show up with these finite element models or any other ones, they don't have the theoretical background, the necessary one, and they're kind of skeptical. But as you know, time moves on, that slightly changes. So that's why I'm, over the years, even the last 10 years I've been giving this course, I'm kind of shifting the ratio based on what feedback I get from former students working in the field. So now it's at 70-30. Probably next time it's going to be like 65-35. So I want you to read the analysis methods, whether one-dimensional, two-dimensional, but most of them say, and if we just kind of look from the beginning, limit equilibrium methods, numerical methods such as finite element or discrete element can be used, but this is left for the experts. Same one, 2D limit equilibrium methods, limit equilibrium methods even for toppling. For the last one, for rockfall, there is no limit equilibrium method. Embankment, seepage analysis, and limit equilibrium methods. Limit equilibrium, limit. So at the time when this was put together, I believe now it's about almost 20 years ago, from the original text, original book, it was limit equilibrium, and anything more sophisticated was left for the experts. Now that has, went from 95 to 5, now we're down at 70-30%. So still, limit equilibrium ones are the governing ones when it comes to offices. Now, one thing that I do have to say, no matter what method you're using, and this is what you're accustomed to generally is, that you will calculate based on the weight of the rock and based on the shear strength, you will calculate a single factor of safety, right? Factor of safety is 1.3, and you call it, that's it. And this is a deterministic analysis. All the parameters have a single unique value, right? That's what you sort of think of. Unit weight of the soil is such and such, or cohesion is such and such. But when we discuss the actual volume, why we over-designed it by 50%, many of you said that all the uncertainty in the parameters. So now, in these days, it's definitely, the split is now, I would say, about 40 deterministic and 60 probabilistic analysis when it comes to establishing a factor of safety, even with limit equilibrium methods. Now, what do I mean by all this? You do appreciate that almost all the input parameters, they have a range of values. Say the cohesion of the soil goes from 10 kilopascals to 14 kilopascals with any volume pretty much in between. We don't really know where the phreatic surface is. It could be higher, it could be lower. The actual load put on the soil or rock varies. Let's say there's a road on top of it, high traffic, low traffic, they add another lane, whatever. Snow conditions, add extra load. All sorts of things that drive us towards defining the parameters that are used in the stability analysis. Not a single values, but some kind of a probability distribution. So let me ask you the question. If I give you 10 samples of soil and you go to the lab, it's the same kind of a soil, what kind of a values you're going to report back for, let's say, their cohesion and friction angle? It's the same soil. Table? Yeah, but what are the values in a table you look like?
The poorer, the most likely, that's the most optimistic.
Okay, somebody else?
I will report the average plus the standard deviation.
Anybody else?
You report the smaller values.
Okay, anybody else?
Report the lowest value 3 sigmas for just so have like over 99% of all the values like covered.
So all of you say is that they're not going to report a single value. Each and every specimen will have its own CN5, right? Now, the big question is how do you deal with these values of 10 different values? Hopefully they're not that far from each other, but once you plot them up, you end up with some kind of a distribution. How do you report it? He says the average, the lowest and the highest, you say the lowest. One says the mean and standard deviation. All of these represent the data. Now, if you take the lowest one, which would yield the safest design, you still get fired. Why would you get fired?
Because it's too conservative.
Yeah, meaning it's going to be really expensive. But he likes the safe life. He gets the smallest value. His design is good, but he gets fired because it's too expensive. So, moral of the story is you would end up with some kind of a distribution of values. I'm just drawing a Gaussian or bell-shaped curve. So it would be the mean, and it would be the standard deviation, right? If it's a normal distribution. That could be all sorts of distributions, but let's go with the simple one. And even these variables or input parameters change, not only in space, right, at the various locations under the dam, but of course they can change in time too. Seasonal variations of the water table, whatever, changes your location of the phreatic surface. So how do you deal with this? Well, we go from a deterministic computation into a probabilistic one. And the way we do it is that each of these parameters now are not defined by a single value, but by defining some kind of a distribution. And from this distribution, randomly from each distribution, you sample it, and then you calculate the factor of safety for that combination of parameters, and you calculate the factor of safety for the slope. And then you do it again. You pick another set of values, you calculate the factor of safety, and you do this over and over and over and over again till you feel that you have sampled all of them, so you have all the combinations of parameters. So this could be, 10,000, 100,000 different combinations. And at the end, you end up with 100,000 factors of safety that you can plot out. So you end up with a distribution of factor of safety. So you end up with something like this. So on average, if I consider now the average value of each of these parameters, and maybe I have 10 of them, one for C, one for phi, gamma, whatever. If you take the mean value or the average value of them, you would end up with the average factor of safety. Okay? But because you picked on random from each of them, you would end up with perhaps a portion of them that their combination results in a factor of safety that's less than 1. Now, we all know that for these distributions, when they're normalized, the area under the curve is 1. Right? So if I've done 10,000 simulations and I count how many simulations resulted in a factor of safety of less than 1, and I divide that number by the total, that tells me the probability of failure, i.e. how many cases the slope failed. So I can say from this one that on average, the factor of safety is one number, but based on the probability of failure, there are combinations that will result in failure of the slope, and I express them as a percentage. So if I tell you that the slope is now has a factor of safety, mean factor of safety of 1.3, and a probability of failure is 8%, what does it mean?
If it failed, still because of that 10%.
Yeah, but what does it mean? Is it a safe slope?
Yeah.
Unsafe slope?
Failed slope.
Failed slope?
Since if the forces increased by 30%, the failure chance is 8%.
So, it says that on average, the slope has a factor of safety of 1.3. However, in 8% of the cases, which are combinations of parameters, the slope has a factor of safety of less than 1. So my question is, what does this mean?
9% chance of failure.
Okay, so
There's 8% of the slope that can fail in a section.
you can interpret it that way. If that section is built up of all the parameters that are at the lowest values, right? Anybody else? What could it mean?
Well, it's like overall you're safe. It just so happens that there is a certain number of combinations that would result in failure, but overall you're safe.
Yes, so on average, the slope is safe. However, 8 times out of 100, it can fail. Now, is that 8% acceptable or not acceptable? To you, it's not.
It depends on the use.
So you as an engineer, and I said exactly the same thing to my undergraduate class last night, you as an engineer, this is where your input and kind of judgment stops. 1.3, 8% failure. It is really at the stakeholders' hand to decide whether the 8% is acceptable or not acceptable. Right? So it really depends on a project. If this is, say, a slope in a remote area, that somebody's cottage, that they go out to the cottage maybe 3 times a year, the likelihood of that slope failing while they're on the road there is remote. So 8% is okay, maybe. If the slope is somewhere, say, on a stretch of a fairly busy highway or next to it, probably the 8% is not acceptable. Right? So this is not really your decision as an engineer. You report it, and whoever decides, they decide whether that's acceptable risk or not. And I'm not sure if it's a big blur now. I try to use this extreme example in all of my classes. I'm pretty sure I said it to the undergraduate class that are you aware that quite a few engineers work for insurance companies? Maybe I mentioned it in this class already. Yes? No? No. So some of you may end up working for insurance companies. Engineers working for an insurance company. Why would that be the case? They pay well.
But you have the knowledge to assess risk.
Yes. You have the technical knowledge to, in this course's content, you establish the probability of failure and a factor of safety of the slope. Let's say the slope is by a busy highway and you're calling the insurance company to get a quote for your car insurance. They ask you, commute for work or for leisure. Okay, what route are you taking? Oh, and based on this guy is driving by all the dangerous slopes that have a higher risk of failure, probability of failure. Therefore, we're going to increase his insurance because the likelihood of him getting an accident and getting killed or claiming anything from us is much higher because the probability of those slopes of failing is higher. So if you say that, no, I don't like that, I'll go on a flat terrain and everything, then okay, let's have a lower insurance. Again, this is a kind of funny example, but it goes to the point of why insurance companies need engineers to calculate risk related to these projects. And how do they assess risk, say for slopes? The probability of failure. You know, it's for them, it's a bad business if you claim money. So that's how engineers work for insurance companies. So it's a whole new field of jobs that are out there. You never knew that they exist. Yeah, you see, the same idea with medical doctors. Think of it that way. If a medical doctor is not that good, they do mistakes of one patient at a time, right? You know, the surgeon and cut something the wrong way. Civil engineers, if a slope fails, you kill hundreds right away if you haven't done a good design. So, you know, a doctor making a mistake is much smaller risk than a civil engineer moving something up. So everybody clear on what this figure is, what it represents, what could be learned from it, and how we interpret it? So we talked about it, just to summarize it. What is the acceptable probability of failure? Well, you as an engineer, you don't know. It depends on the project, the volume, the risk.
Don't you have like certain guidelines for that in like building codes or like say highway design codes?
Yes, but it depends on a project. You might have a different guideline or different, I'll show you a figure a little bit. I guess the next slide from the other course. That it really depends on a project. You can't have the same thing applied for all the potential. So you know, it's the same road, but a rural road as opposed to an urban road. It's a road. Okay, so let me just find that other set of slides just to show you the risk. Take me a moment to find a chapter off the top of my head right now. I'm guessing. No. So, going on this, going rockfall. Doesn't matter what it is, how the risk assessment is done. This is a rock fall, basically large boulders detaching and falling off a rock face. How the risk is assessed. If the rock fall itself is precipitated by rain that lowers the friction under the base of that rock, and that's why the rock falls off, looking at the first one, 33% of a year, and this was in BC, right, so it rains a lot. In any given year, 33% of the days it rains. So the failure occurs when it rains. Now, simultaneously, when it's raining and it starts a rock fall, in 95% of the times when it's raining, there is no rock fall. Therefore, nobody dies. However, when it's raining, in 5% of the cases, there is a rock fall started by. Okay? When it's raining and there is a rock fall, if there is a vehicle on the road, in 98% of the cases, there is no vehicle. In 2% of the cases, there happens to be somebody driving by. You have a 50-50 chance, according to that, the impact being significant, i.e., you become a pancake or not, 50-50 chance. So if one person was in a vehicle, your chances of dying in that case is 50-50. If there are two people, well, your chance less, or somebody dying is less. 3 or more is less. So when you multiply all these things out, this is the annual probability of fatalities precipitated by a rainfall, rockfall, and so forth. Okay? And I want to show another figure. What is the acceptable risk? Various companies, and this was for I believe, for roads and rockfalls nearby. And I'll try to make it a little bit clearer. So, let's say UK. They have the guideline of number of fatalities versus the annual probability. They developed this line here, that the risk 10 to the minus 5 probability for 1,000 people a year in the whole British Isles dying from rockfall is something like that, versus 10, it's 2 orders of a magnitude less, or 1 is even an additional. So they accept this level of risk. The Netherlands, they have a very different set of guidelines. So the Brits don't value their citizens as much as the ones in the Netherlands. Because say for one person, the cost of life is the same, but the Brits don't care that much for 1,000 a year than say the Dutch. The Dutch say it has to be 10 to the minus 8 probability for 1,000 people dying. The Brits say, we're okay with 10 to the minus 5. Okay? So now this is the table that he referred to as far as guidelines. Different countries, different. Now in BC Hydro and Hong Kong, they accept this line here to be what's deemed to be safe. So when you go through this exercise of calculating the probability of occurrence of an event leading to a fatality, this is the guideline that you have to adhere. So for this particular road cut that we looked at in a previous set of slides, it plots somewhere here. So it is either meeting or exceeding the proposed BC Hydro, and it's even better than the Dutch are doing. So that would be an acceptable situation, as much as engineers come up with these guidelines. Okay, so it's putting everything in context. Any thoughts, any questions about this? These slides are. I'm just showing examples. These for different courses. These are just examples. You don't need to know about them. This is just to illustrate that. I guess it's time to wrap up the show. So, as I mentioned, when you're studying for the midterm 2 weeks from today, it's up until the break. But I started after the break and onwards is the material for the second. All the proposals are in. I'm going to read them, and hopefully by next week I'll give it back with a grade and perhaps comments. Still, you can write